example problem from section 8.3. So we have a capacitor and an inductor in series. After this switch opens, all of this is gone, and we want to look at how this drains out. All right, so let's look at our t less than 0, because we need to get our initial conditions. So t less than 0, it's a DC circuit. Switch is closed. Capacitor looks like an open. Inductor looks like a short. Whoop. We want I and V. What's our initial current? Well, there's a big hole. Big hole, no current. Initial voltage. This resistor is just dangling, so it's like it's not there. So the voltage across here is what we're interested in. We can use voltage division. 40 over 40 plus 10 times 20. That gives us, I don't know, 16 volts. Cool, okay. Do we need DI or DV? We don't know just yet, so we're going to hold off on finding those, and we're going to kind of do that on the back end. So let's look at t greater than 0. And I thought I picked a different color, but I guess I didn't. Where's all my colors? No. Okay, that is a different color, even though it looks exactly the same. Whatever. I seem to be missing a color, but oh, pink. Let's use pink. We're doing this. Okay, we're good now. Marker's worked out. So the switch opens, and we just have this side. This is just after the switch opens, so our inductor and our capacitor do not look like shorts and opens. They look like themselves. Right there. Okay, so let's go ahead and call this VC and this VL, so we don't get ourselves mixed up. And the first thing I want to do is calculate alpha and omega naught. So alpha for a series RLC circuit is 2L, R over 2L. So that's 40 plus 60 over 2 times 2.5, or 20. Omega naught is 1 over the square root of LC. So I have 1 milli times 2.5, square root, 1 over that, and that happens to give me 20. So my alpha is equal to omega naught, and I'm critically damped. Now, I have provided you an equation sheet that hopefully you used in Chapter 7. Now you can see what we're using it for Chapter 8. So there's a box on there, it says alpha equal omega, and then it shows you the generic equation, which is I of t equals A1 plus A2t e to the minus alpha t. Okie dokie. Good. Well, we do have one initial condition that we can go ahead and plug in. Plug in 0 for t. I of 0 is equal to A1 plus A2 times t is now 0, e to the minus 20 times 0. I of 0 was equal to 0. So if I solve this, I have A1 equals 0. All right, got rid of 1 right away. That is super. We like when that happens. Let's go ahead and take our derivative. di of t by dt is equal to, well, it's easier if we go ahead and use the A1 is 0, so we know that we don't have to worry about that now. So we're just taking the derivative of this. So we have to do first times derivative of the second plus second times derivative of the first. So I'll do derivative of the first times the second plus second times derivative of the first. Wait, which one did I do first? I did derivative of the first times the second So now I'm going to do derivative of the second times the first. So derivative of the second times the first. And I'm writing alpha. I could go ahead and put that minus 20 in there. Let's go ahead and do that. So we have a2e to the minus 20t minus 20a2t e to the minus 20t. Okie dokie. So now what can I do? Well, I need this initial condition. And remember that L di dt is equal to VL, or di dt is equal to VL over L. So I need the voltage across that inductor, right? So how can I find that? Well, if I put these in series, I have 100 amps. I can write a KVL around here. So I'm sorry, 100 ohms. I can write a KVL around here. I have I times 40 plus 60 plus VC plus VL equals 0. I know I, that's one of my initial conditions. I was 0. I know VC, again, that was initial condition. That was 16. So I have that my VL is minus 16. So my di dt is minus 16 over 2.5. And that gives me something that I cannot find on here for some reason. I don't have that. Let me grab a calculator real quick. Okay. 16 divided by 2.5 is 6.4. Okay, so that's my initial condition. I need to set this equation equal to that and plug in 0. So di of 0 by dt is equal to minus 6.4 is equal to a2 e to the 0, right? We're plugging in 0 for t, minus 20a2 times 0, e to the 0. So I have a2 is minus 6.4. So now I just need to put everything into the equation, which is lost. Here it is, back into this one. So I have I of t equals a1 was 0, a2 was minus 6.4 t, e to the minus alpha, alpha is 20, t. Then I should write amps. So there we go.